Good day, Evan Snowman here for Umahluko, Making a Difference. Today we're looking at triangles whose sides and proportion that they are similar. Previously, we saw that if we had a situation where we had triangles where one side was parallel to another side, that this thing led to sides being in proportion. We then saw that, we saw that if we had a triangle with one side cut in proportion, so in proportion A and B, and we had a sort of so we had one line that was parallel. This led to sides being in proportion. In other words, we knew then that the side on the right hand side would also be cut into the same proportion of A is to B. Remembering that proportion means equal fractions. So in other words, on the left, A over B would be the same as A over B. Remembering that we then saw that the converse was that if we had a triangle where we knew that these two sides were cut in proportion, so if we had a situation where we knew that these two sides were cut in proportion, such that this was A and this was B, and this was A and this was B, so we knew that if the sides were in proportion, this led to the fact that we now knew that the sides were now going to be parallel to one another. So again, we're going to be looking at this for the current idea. What we've said most recently is that if we have triangles whose angles were equal, so we knew that this angle equaled this angle, for example, equaled this angle. We knew that if this thing was equiangular, we knew that this meant that the sides were in proportion. Well, again, proportion. Okay, let me just quickly put this in there. What we are saying now is, again, the converse. That if I had a situation, I knew something about the triangles. For example, I knew that A, B, and C, D, E, and F. So if I knew that the sides were in proportion, i.e. A over D equaled B over E equaled C over F, then I knew, importantly, therefore, these triangles were similar, or that they were equiangular. Now, please note that it is vital to realize that it is all three. You can't just look at the first two. You can't, this is not enough. This is not sufficient. It has to be all three. Now, admittedly, this is not a theorem that gets asked too often in exams. I have, in my research for today's lecture, I was only able to find one or two real examples, and here's one from an old mock examination from Mpumalanga. We're given some form of quadrilateral with a set of diagonals, and the information that AB is 8, AC is 10, CD is 18, BD is 15, and the one diagonal CB is the length 12. We're then asked to prove that the triangle BCA is similar to the triangle CDB. Now, the first thing I'm going to do is encourage you to make sense of, to ensure that you know which triangles we're talking about. So BCA is this triangle to the top left of the one diagonal, and the triangle CDB is the other triangle to the bottom right of that diagonal. So you're talking about the top left one I've shaded yellow and the bottom right one I've shaded orange. Now, we don't know any angles here. We have no parallel lines. So our normal instinct to look for similarity of using equal angles is not going to work in this case. So I'm forced to use sides in proportion. So let's have a look. Well, generally speaking, and I'm tempted to refer to the fairy tale of Goldilocks, but we're going to use the biggest side with the biggest side, the shortest side with the shortest side, and the midlist side, so to speak, with the midlist side. So if I was to compare 18 with the longest side in the yellow triangle, which is 12, and I was to compare that with the shortest side, which is 8 in the one triangle. Oh, unfortunately, that is paired with the 12 in the orange triangle, and the midlist one is 15 in the orange triangle and 10 in the bottom triangle. Now, hold on. I need to check if those things are equal, and perhaps I should not have been so hasty to write that they are equal. But I do want to emphasize that every single time that I've written something in the numerator, it has come from the orange triangle. So these are all values from the orange triangle, whereas these are all values from the yellow triangle, so to speak, or the triangle that I've shaded in yellow. As I said, the key thing is to see whether these things are in fact equal, and it is not difficult to realize that 18 over 12 is the same as 3 over 2, 12 over 8 is the same as 3 over 2, 15 over 10 is the same as 3 over 2. So we do, in fact, have a situation where these three refractions are equivalent to one another, and as a result, because they are all equal, we now know that the sides are, in fact, in proportion, and because the sides are in proportion, we know that therefore the triangles are similar to one another. So therefore, the triangle ABCA is similar to triangle. Well, let's just go through this carefully. I know that given us the answer BCA is going to go with CDB, but let's just go and check that. Okay. Angle B in the triangle BCA is over here between the smallest side, the 8, and the largest side, the 12. So that must be paired with the shortest side, which in this case of the yellow one would have been the 12, and the largest side, which is the 18. So that would in fact go with C over here. So I would agree that that is a C. In the yellow triangle, the C is between the 10 and the 12, between the longest and the middle length side. So let's pair that with what's happening in the orange triangle. That would be point D, or vertex D. And the third vertex is then left to be B. And I would agree with their situation that it is CDB. And the reason here is because the sides are in proportion. Again, being a geometry, I've given my reasoning. 9.2. Hence prove that AB is parallel to CD. Well, remember, we are saying that if the sides are in proportion and these triangles are then similar, we know that the angles are equal. But we've just gone and shown it in the picture as we were checking that angle ABC, therefore, angle ABC is going to equal BCD because the triangles were similar. But if those two angles are equal to each other, then we have an alternate pair, and therefore we know that that length AB or side AB will be parallel to side CD because alternate angles are equal. Okay, so 9.2 followed quickly on from 9.1, and generally speaking in an exam, I think the mark allocation would have given you a good indication of that. Okay, I'll get to a question that I actually quite enjoyed when doing in preparation for today's lesson, and so we need to think about what happens if they now ask us about Okay. Knowing that we have now got the situation where these lines are parallel, and so we now know that because these lines are parallel, we know that the top angle is equal to this bottom angle over here at C. We are now going to follow on to try and show the length of CE. Now, my problem with CE is that it is not an entire length. It is a piece length of within this diagram. It is not the length of an entire diagonal. It is only a part of the diagonal. And so what it struck me was actually what I needed to consider was CE being that piece of CB, which meant that I had the remaining piece over here of BE. Now, for its experience, but I now know that I need to use a triangle that contains CE and another triangle that contains BE. And I could initially consider doing the following: the triangle on the left over here and the triangle on the right. But I realized quite quickly that I then don't have sufficient information to prove anything about this, to prove anything about these two triangles, the one on the left and the one on the right. So what I'm going to choose to do is I'm going to choose to instead focus on the top triangle and the bottom triangle. Those two triangles there, one with the squiggle and the one with the shaded lines. The reason I'm doing this is because I have already got that extra fact of that angle at B being equal to that angle at C, which I've marked with a red dot. Now, because these lines are parallel, I have another pair of alternate angles. And so what I have here now is a situation where I also have this pair being alternate to one another. And because these lines are alternate to one another, I can show that those two triangles, the one with the blue squiggle and the one with the blue shaded marks, are similar to one another. So it's going to take a while quickly. So in triangle ABE and triangle CDE, one, we've already shown that ABE equaled CDE DCE, proven above. I now know that BAE, so handwriting, is equal to EDC, alternate angles on parallel lines. And therefore I know that triangle ABE is similar to triangle, and again, let's get the order. A is the one with the X, but be marked with the X, so it goes with D. B is the one with the dots, so it's marked with C. And again, it would have been quite easy to realize that E is vertically opposite, and so that I could have used that as a pair of equal angles. And this would be angle, angle, angle. The consequence of proving that these triangles are similar is we then know that AB over DC equals BE over CE. And what I'm going to do now is I'm going to say, cool, since I don't know the length of CE, I'm going to let CE equal X. As a result, it must follow that BE equals 12 minus X. So what I have now is, if I substitute back in the values, I've got 8 over 18 equals X, sorry, 12 minus X over X. If I cross multiply and sort out my things, I got 8X equals 216 minus 18X. And it will follow, hopefully you'll get there, that X will equal 216 over 26, which is approximately equal to 8,3. And again, we have then solved for the length of CE. You could leave it as a raw fraction, 108 over 13. You can't simplify any further than that. Or you could write it down as a fraction to 2 decimal places as per the exam instructions. Okay, so now since we've got some extra time, I thought I'd look at another example from an old exam paper, albeit that this one does not have the proportion idea, but we do have the similarity and it has some interesting ideas in it that I'd like to consider. So for 10.2.1, we are asked to prove that triangle AEF is similar to triangle AMD. But again, I'm going to read through the text first and take note of the fact that they tell me that we have a circle center over here at M. They tell us that these things are perpendicular, which is important, and they tell us that these angles here are equal to one another because that the angle is bisected. We're then looking at triangle AEF, the one that I've done here with the dashed lines, and AMD, the one that I'm marking here with the dots. So let's consider what we have here. Well, we have the fact that A1 equals A2. That's quite a clear fact. We do have that D1 is marked as right-angled. If only we had a right angle in the striped triangle, AFE, which we do if we think about the fact that point M is the circle center, which as a consequence means that AE is a diameter, and we should know that angles from a diameter are 90 degrees. So we can do this one quite quickly. So 10.2.1 in triangle AEF and triangle AMD. 1, we know that A1 equals A2, given. 2, we know that F equals 90 equals D1, which is 90. We know that F equals D1, which is an angle from a diameter. And we know that D1 equals 90 because it was given to us. So we now have, again, we have two pairs of angles that are equal. Again, please ask your local teacher. Some provinces are quite strict about this, other provinces are not as strict, whether you need the third fact, which comes with angle sum of a triangle, or 3 angles of a triangle equal 180. But what we do get as a consequence is that therefore triangle AEF is similar to triangle AMD. Okay, looking at question 10.2.2, which should follow on from 10.2.1, we are asked to consider AF and AD. AF is this pair over here, and it would go with AD. So we have the fraction we wanted from earlier, and we're going to pair that then with either AE and AM, or we're going to pair it with EF and MD. Now, I'm going to choose to pair it with AE and AM because I'll show you now. We know that AE is the diameter, and we know that AM is a radius. So we know that AE is 2 AMs because it is the diameter. So what I'm going to get here is 2 AM over AM, which gives me an answer of 2. AF over AD has a ratio of exactly 2. Okay, we're now asked to look at AD squared being paired with CD times DE. And what I'm going to do here is I'm going to show you a technique that I encourage my students to use, which is to mark what I'm talking about. So AD squared means I'm using AD twice. I'm then looking at CD, and I'm looking at DE. So DE is this one over here. And I've got CD and AD marked twice because of the square. We know it is going to be used twice. So what I'm looking for now are two triangles that involve as many of these sides as possible. I have taken the green shading out for a moment to try for clarity. And what I hope you can see is that if I was to consider this triangle here, triangle AED, then what I'd then have is two of the sides. So I know I'm going to be looking at triangle AED, and I need to look at another triangle that contains as many of the others as I can. And it looks as though the only triangle that is going to use CD, or the only one that's going to use CD over here, is going to be this triangle that I'm shading in a little bit more thoroughly over here, triangle CDB. And although it doesn't use a second of the red stripes that I've drawn earlier, we just need to have some faith and see if that doesn't come out as part of our proof. There must be a reason why this is the third of the questions, not one of the earlier questions. Normally, as you have enough experience to know that questions very often get a little bit more difficult as we go along. So I'm going to look at triangle CDB. Well, let's have a look here. I know that in this triangle, I know that A2 is going to equal angle C, because they are angles from the same chord, angles from the same arc. In this case, the chord EB, even though the chord has not been drawn in. Secondly, I know that D1 and D2 is the same size as D4, because they are vertically opposite. I apologize for the handwriting if this device is writing a little bit blurry at the moment. The third one would be also that E2 equals B if I needed it. Because of angles from chord AC. I then have that triangle AED is similar. A is paired with C, E is paired with B, D is paired with D. So we got it in the right order. Angle, angle, angle. And as a result, we should now know that, therefore, AE with BC is equal to AD with CD is equal to ED with BD. And again, I just want to show you again what I want to do. I want to go and check that I've got the right things here, so I'm going to mark them off here. DE is this one here, ED, it's the same line. CD is this one here. That tells me that it is these two pairs, that is this pair that I'd like to consider. So I'm going to cross multiply and see what happens. I'm going to choose to ignore for the moment the left-hand fraction because it doesn't seem to be relevant. I'm going to choose for a moment to ignore that one, having identified the pieces on the other two pairs, and I'm now going to proceed to cross multiply. So I've got that AD times BD equals CD times ED or DE, the same thing. Hold on. We said we want to get AD squared. We have the CD times DE on the right hand side, but we don't quite have the AD squared on the left hand side. But we should know that BD is the same length as AD because we've got a line from circle center to perpendicular to chord. Sorry, I just need to quickly undo that last bit. So perpendicular to chord. So that was theorem 1. And unfortunately, we don't see it so often, and so we very often forget the very first theorem we did in grade 11, which is that if a line was perpendicular to a chord, it bisects that chord. As a result, we've got what we wanted, which is that AD squared equals CD times DE. And we are done with that example. Thank you very much for your time today. We'll see you soon, hopefully.